The title of this talk is Injection Secure Structured Encryption and Searchable Symmetric Encryption, and this is joint work with Ghosh Amjad and Tariq Muataz. So in the problem of encrypted search, we have a trusted client that has a private data set that it wants to outsource to an untrusted server. So we want to design encryption schemes that allow the client to encrypt the data before it sends it to the server in such a way that it can later send a query and have the server answer this query without having to decrypt the data. So there are a variety of cryptographic primitives that one can use to design encrypted search algorithms, including fully homomorphic encryption, property preserving encryption, structured encryption, oblivious RAM, and functional encryption. So in this talk, we're going to focus on structured encryption. And so these are encryption schemes that allow a client to encrypt the data structure. So there's a setup algorithm that takes as input a security parameter and the data structure, and it outputs a key and an encrypted structure that can then be sent to the untrusted server. And then at a later point in time, when the client wants to query the data structure, it runs a token algorithm with the key and its query. This generates a token that it sends to the server, and then the server can execute a query algorithm on the encrypted structure and the token in order to get an answer that it can send back to the client. So when we're thinking about the security of these schemes, we're interested in how much they leak. And so in particular, we're interested in the setup leakage, which is the information that the server can learn just by looking at the encrypted structure. And since we support a query operation in this particular example, we're also interested in the query leakage, LQ, which is the information that the server can learn by executing the query algorithm. So depending on the operations that we support, right, if we also support an add and a delete, then we'll also want to consider the add leakage and the delete leakage. And so typically we'll say that a structured encryption scheme is LSLQ, LA, LD secure if it reveals no information about the structure beyond the setup leakage, and if it reveals no information about the structure and the queries beyond the query leakage. And the same thing for the add operations and the delete operations with respect to the add leakage and the delete leakage. So there are many different types of structured encryption schemes. There are schemes that are designed specifically to encrypt arrays, to encrypt dictionary data structures or multimaps, range multimaps, encrypted graphs, etc. So in this work, we're going to be concerned with multimaps. And the reason is because multimaps are the basis for most of the encrypted, or a lot of the different types of encrypted search algorithms that are of interest. So just as a reminder, what a multimap is, we'll start with a dictionary. So a dictionary is a data structure that stores label value pairs, and they support get operations. So for example, if I want to do a get on label 3, the dictionary will return to me the value that is associated with label 3, in this case, V2. A multimap is similar to a dictionary, but instead of storing label value pairs, it stores label tuple pairs. So you can see an example here. And they also support get operations. And so if I want to do a get on label 3, then the multimap will return to me the tuple associated with label 3, which in this case is V2 and V4. So there are many different ways of encrypting multimaps. Here we're particularly interested in dynamic multimaps. So these structured encryption schemes have to support not only gets but also puts, or maybe adds, edits, different types of update operations. And so most of the schemes that support, or most of the dynamic encrypted multimap schemes that support optimal time queries have a similar leakage pattern. In particular, the leakage that is revealed at query time, so the query leakage, typically reveals what we call the query equality pattern, which is if and when two queries are for the same label. Okay, so you may not know what the label is, but you know that these two queries were for the same label. And they also typically reveal the add query equality. This is for the add leakage, which is if and when an add is for the same label as a query. So in this paper, we introduce a new representation for leakage, which is particularly useful for the kinds of problems that we're considering here. And so we call these leakage graphs, and I'm just going to give an example of what this looks like. So with the leakage graph, essentially what we do is every operation that happens on the encrypted structure is represented as a vertex, and we add edges between vertices depending, or if a correlation between these two operations is revealed by the leakage patterns. So in this case, The ad leakage is the ad query equality, which we saw before, and the query leakage is the query equality. And so now suppose that my first operation is a query on label L5. At this point, the server wouldn't know anything except that I made a query. It wouldn't know the label that I queried on. And then let's say that my next operation is a query on label L2. So again, it just knows that a query occurred. And then, but now let's say that I do an add on label 5. In particular, I want to add the value 2 to L5's tuple, right? So in this case, because my scheme leaks the add query equality, then the server is going to know that the third operation is correlated with the first operation. So it will not know the label, but it will know that these two operations were for the same label, okay? So now, suppose my next operation is a query on L5. And so again, because this scheme leaks, or because this particular leakage profile reveals the add query equality, the server will know that this fourth operation is for the same label as the third operation, right? It doesn't know the label, but it knows that they're the same. Okay, and this is represented by this edge. And now suppose, because because the scheme also leaks the query equality, then the server will also learn that the fourth operation is for the same label as the first operation. Okay, so it gets an edge between these two vertices. Okay. So in 2016, Zhang, Katz, and Papamantu introduced a new type of leakage attack, which is called an injection attack. It's an active attack. And these attacks can be run on any scheme that have a ad leakage that reveals correlations between ads and queries, okay? And the idea is roughly as follows. So suppose the server sees, suppose I make a query on some label, right? The server is going to just knows that there's a vertex. It doesn't know what label is being queried. And then I do another query. Again, the server doesn't know for what. But then suppose that the server can trick the client into doing an add operation for an adversarially chosen label, in this case, L5, okay? And we're going to call this an injection. And we'll call all of the queries that happen before the injection pre-injection queries, and we'll call all of the queries that happen afterwards post-injection queries. So now, because this leakage profile reveals correlations between ads and queries, then the server, when the injection happens, the server will know that its ad, for which it knows the label, is correlated with the first query, right? And so because it knows that this ad was for L5, then thanks to this edge, it knows that the first query was also for L5. So now it knows what label the first query was for. Okay. And if I keep querying, and these are the post-injection queries, and then let's say, suppose my last query was also for L5, then this leakage profile will reveal this correlation, the correlation between the injection and the last query. And because the adversary knows that the injection was for L5, then it knows that the last query was also for L5. Okay, so this is the idea behind injection attacks. So in 2014, Stefanov, Papamantu, and Xi introduced the notion of forward privacy, and it wasn't quite formalized, but the intuition was that adds and deletes should not be correlated with previous queries. And so this was formalized by Boss in 2016, roughly as adds and deletes should leak only the size of the operations. This is, it's roughly this. And then it was formalized, or we formalized it with Tariq a little bit differently, where we said, okay, well, let's formalize it as adds and deletes should leak nothing. And so one of the observations from Zhang et al. Was that this notion of forward privacy that was introduced a few years earlier, it actually protects pre-injection queries, right? So if you're trying to do injection attacks against a scheme that is forward private, then the injection attacks will not be able to learn, or the adversary will not be able to learn any information about the pre-injection queries. Okay, but it will still be able to learn information about the post-injection queries. Okay, so this was observed by Zhang et al. And so to see why, let's do another example. So suppose again I'm doing the same sequence of queries. I do my injection, right, or the adversary does an injection. So normally, if you had a scheme that was not forward private, then the adversary would learn a correlation between this injection and the first query, right? But if the scheme is forward private, then this particular correlation will not be revealed. Okay. However, if I keep querying after the injection, then the scheme can reveal correlations between the ad and future queries. Okay, so in this case, and so forward privacy will not hide these correlations. Okay. So one of the things that we observe in this paper is that even though forward privacy is a useful notion, it has some limitations, right? In particular, if you have a scheme that leaks not only query to ad equalities, but also happens to leak the query equality, which a lot of schemes do, which as we've seen a lot of schemes do, then an injection attack, you can still use an injection attack to learn pre-injection queries. Okay, so really forward privacy is not necessarily enough if you also leak some other leakage patterns, because you can just combine them, right? So in this particular example, if I do my injection, I may not be able to correlate it to the first query, that's fine, but I can correlate it to the last query, right? Forward privacy doesn't prevent that. And because I also leak the query equality, I can then use the query equality to correlate that last query to the first query, right? And then I just follow the path, and I know that the first query was also 5. Okay, so what's going on? So essentially, what's going on is that injection attacks are only a subset of a larger class of attacks, and forward privacy is only one security notion among a class of related notions. And so one of the things that we do in the paper is we introduce the notion of a correlation attack. And the way that correlation attacks work is essentially that the adversary first learns the labels of a subset of operations. And this can be done using injections, but it doesn't have to be. An adversary could do it based on inference attacks or known data attacks or any other type of attack. And then it uses leakage to correlate known operations with unknown operations. And operations here don't have to be queries, right? They could be anything. They could be adds and they could be deletes. Okay. And injection attacks are really just a special case of this larger class of correlation attacks. And in particular, the correlation attacks where the adversary learns the labels of a subset of operations by essentially adding these operations. And in particular, uses add query leakage to correlate adds to unknown queries. Okay. So in the paper, we provide a security definition against correlation attacks, which we call correlation security. I'm not going to formalize it here. It's a bit complex. But the sort of the high level intuition is that we'll say that a particular leakage profile is correlation secure if it doesn't reveal correlations between certain types of operations. And this can be thought of more intuitively as if the leakage graph of the profile has, doesn't generate paths between certain types of operations. Okay. And we can formalize injection security as a special case of correlation security. And in particular, we'll say that a leakage profile is injection secure if there are no paths between adds and pre and post injection queries. Okay. Okay. So now I'll mention that there are other ways of achieving this kind of security. One could use ORAM. So you could store your multi-map in an ORAM, but you have to do it in a volume hiding way. And so we have some discussion about how one could possibly do this in the paper. And there's another approach. There's a scheme called Swiss. So this is not just a multimap, unencrypt the multimap, it's a SSE scheme, which is a different primitive. There's an argument as to why it provides injection security, or it's secure against injection attacks, but there's no security definition for injection security. So it's more just of a, it's more just of an argument. Okay, so moving on to the contributions of the paper. So one of the things that we prove in the paper is that we show that if a leakage profile is such that it only leaks the query quality, right? So its only leakage is that it reveals if and when queries are for the same label, and it leaks nothing else. In particular, its add and deletes don't leak anything, then it's injection secure. So that's the first thing that we prove. And then we design a scheme, we design a crypto multimap that has exactly that leakage profile. Okay. This new multimap encryption scheme is called FIX, and it's the first dynamic injection secure multimap encryption scheme. And then based on that, we design an SSE scheme, which we call FIX SSE, which is a dynamic injection secure searchable symmetric encryption scheme. In order to do this, we have to design a few different building blocks, and one of them is a dynamic volume hiding multimap encryption scheme, which we call DVLH. And that itself is based on a dynamic pseudo-random transform, which we call DPRT. And all the schemes above it can achieve sublinear search, sublinear time search over certain assumptions on the workloads, right? So for certain assumptions on the data distribution and the query distribution. So so this is a visualization of the schemes that we propose in the paper and kind of the relationships. So we have an SSE scheme that is built based on our multimap encryption scheme, which is called FIX, which is injection secure. FIX itself makes use of two multimap encryption schemes. It makes use of a static volume hiding multimap encryption scheme and of a dynamic volume hiding multimap encryption scheme. The static scheme VLH itself makes use of a standard multimap encryption scheme and of a building block called the pseudo-random transform, which we introduced in an earlier paper. And the dynamic volume hiding multimap encryption scheme makes use of a standard dynamic multimap encryption scheme and of a dynamic version of the pseudo-random transform, which we introduced in this paper. And for the talk, I'm going to focus just on the injection secure multimap encryption scheme, so just on FIX. The way the scheme is going to work is that we're going to stash, add, and delete tokens locally at the client, and we're only going to push them according to a schedule that is random and fixed. Okay. And this random schedule is going to be determined by a random permutation pi, right? And so, of course, because we have a stash, then it's client-side state. It can grow, and it's going to grow as a function of how the adds and the deletes are distributed. But in the paper we show bounds. We give upper bounds for different types of distributions. Okay, so the scheme makes use of two building blocks. It needs a static volume hiding multimap encryption scheme. And so what volume hiding means essentially is that if I query the multimap, the server will return to me the tuple without learning the size of the tuple that it's returning. And this can be instantiated using a variety of constructions. And it also needs a dynamic volume hiding multimap encryption scheme. So in particular, an EMM that's volume hiding, but that also supports deletes and inserts as well. We use two particular schemes in the paper, one of which we introduce, and both schemes are volume hiding, but also reveal the query quality. Okay, so the scheme at a high level works as follows. So we start by sampling a random permutation pi, and we create two empty multimaps, MMMN, which is for new, and then MMMST, which is going to be our stash, right? So there's going to be a local multimap that we're going to keep locally at the client. and then we also have a counter. So we're going to take our input multimap MM, and we're going to encrypt it with a static volume hiding scheme, which is going to give us an encrypted multimap EMMO for old. And then we're going to take our empty multimap, and we're going to set it up with our dynamic volume hiding scheme, which is going to give us an encrypted multimap MMM new. Okay, and our injection secure encrypted multimap now is going to be composed of these two EMMs: EMM0, which is static, and EMMN, which is dynamic, both of which are volume hiding. Okay, now suppose I want to append a tuple of values V to a label L. So I'm going to first take the tuple of values V, and then for each value in this tuple, I'm going to concatenate a flag to the value, and this flag is going to just be an add flag. Okay, and then I'm going to store these flagged values to my stash. Right, I'm going to store them in my stash. I'm going to store them in my local multimap. I'm going to associate them with the label L. Okay, and then I'm going to run a push algorithm. I'm going to describe how the push algorithm works later. Okay, so that's it. So the add protocol is fairly simple up to this point. Now, suppose I want to erase values from L's tuple. So I'm going to do something similar. I'm going to look at all of the values V in the tuple that I want to delete, and I'm first going to check my stash. So I'm going to say, okay, do I have a flagged version of the value V in my stash, right? If I do, I'm going to remove it from the stash, right? And if I don't, then I'm going to add the value V to the stash with the flag delete, right? With the deletion flag. Okay. And then I'm going to run the push protocol. Okay. So again, this is fairly simple up to this point. Okay. Now, suppose I want to do a get. So one of the challenges with the scheme is that we have a static EMM. We have stash, which is local, and then we have our dynamic EMM. And they each have a different version of the data that we're interested in. So we're going to query all three, and then we need to kind of reconcile the answers, right? So that we get the correct results, because some of these structures are going to be out of date. Okay. So the idea is the following. So the first thing we do is we're going to query the static EMM, and we're going to get a set of results, RO, right? And these results could be outdated, right? There could be items in there that we've deleted, but since the structure is static, we've never actually removed it from that structure. Okay. Then we query the dynamic structure, and we get back a set of results, Rn. Okay. And then what we do is we compute the following sets. So we generate a set R+, which consists of all of the values in the stash, or all the values for L in the stash that have an add flag, right? So these are values that we've added, but that never got pushed or haven't been pushed yet. Okay. And then we do the same thing for the deleted values. So we look at all of the values in our stash for L, and we find all the ones that have a deletion flag. So again, these are values that we wanted to delete, but haven't been pushed yet. And then we look through our stash again, and we find all of the values associated with L that have a deletion flag, but also an old flag. And this will make sense when we get to the next step. Okay. And then our result is basically going to be the union of RO, so the results that we got from the static structure, with the results that we got from the new structure, and the results from R+. So these are the values that we've added in the stash, but that haven't gotten pushed yet. And then we remove the values in the stash that have a delete flag, and the values that have a delete and an old flag. Okay. And if you sort of work out the details, you can see that this outputs the correct result. Okay, so I'm going to give just a high-level explanation of how the push protocol works. So the high-level idea is that so for any label L, we have values that are associated with L that are stored in the stash. And some of them are values that need to be added, and some of them are values that need to be deleted, but haven't been pushed yet. And then we also have values associated to L that could be in the static EMM that is stored on the server, and on the dynamic EMM that is also stored on the server. So the idea behind the push protocol is that it's going to pick a set of label tuple pairs, mu of them, and those will be picked at random according to the random permutation pi, and it's going to recover all of the values associated with one of the labels from the static EMM and from the dynamic EMM. It's also going to then query the stash to get back the values that need to be added that are associated with them, the values that need to be deleted to be associated with them, and it's going to merge all of this. It's going to merge all this information and create a new tuple of values that is updated, right? A correct tuple of values, if you will. And then it's going to push this new tuple to the dynamic EMM stored on the server, and then it's going to erase all of the values associated with L from the stash. And yeah, that's pretty much it. And again, it's going to do this for mu labels at a time, and those mu labels are going to be determined. Which mu labels get pushed in which epoch is going to be determined by the random permutation. Okay, so I'll briefly mention the leakage of the scheme. So the setup leakage is the size of the input multimap and the size of the label space. The get leakage is the query quality pattern, and inserts and erases are leakage free. The efficiency of the scheme, if we push label tuple pairs in batches of size log n, then the get complexity is logarithmic. The insert and erase complexity is polylogarithmic. The scheme requires 2 rounds of interaction. It's stateful, obviously, and also depending on the underlying volume hiding schemes that we use, it can be lossy. And we also have an analysis in the paper of the size of the stash. Yep, and that's it. Thank you.